Hi everyone, this is Professor Monty, and today we're going to talk about ANOVA. So let's get started real quick. First of all, we talk about the F distribution. When we do a hypothesis test for ANOVA, it's based on the F distribution. So they start off this chapter just talking about this distribution. We'll just talk about it briefly, but essentially the distribution looks like this. So we've got this F distribution. We'll talk a couple things about it. Note, for the F distribution, we see that, first of all, it's definitely right skewed. And notice it starts at 0. So it's very similar in that regard to what we did with the chi-squared curve. It's not similar to the Z or the T curve that goes forever to the left and forever to the right. It starts at 0 and then just goes off to the right. We do know that the area under the curve has to be 0. And lastly, the curve goes forever to the right, approaching but never reaching the x-axis. So curve goes forever to right. Approaching, but not reaching. We typically call it the x-axis, but they're just going to call it the horizontal axis. Okay, so those are the basic ideas. Notice it's got two different degrees of freedom, the DF. They've got degrees of freedom. It's called degrees of freedom for the numerator and degrees of freedom for the denominator. We'll talk about the numerator and denominator later, but we're not going to go any further into the F curve. I will show you how it relates to the p-value when we get there. But for now, that's all that we need to know about the F distribution. There's tables for it. We're not going to be using the tables in this class. So that's actually as far as I'm going to go for now with this graph. So let's go into the next section. The next section, 16.2, one-way ANOVA, the logic. Okay, so let's talk about what we're doing. First of all, let's talk about a couple things here. First of all, ANOVA. What in the world is ANOVA? Well, ANOVA is an acronym. What it stands for, and I'll capitalize the ANOVA part of it, it's analysis of variance. And so we see from there it's ANOVA. That's where the ANOVA comes from. All right, so it stands for analysis of variance. We'll talk a little bit about where that comes from and what that means, but let's talk about this one-way also. For one-way ANOVA, there is only, oops, I forgot the is. There is only one other factor in the classification. And you may say, what in the world are you talking about? Well, I'll tell you. So we use ANOVA to test the means of more than 2 populations. So think about what we did in the past. We've tested the means of 2 populations. We did that. What we did is, if we don't know the population standard deviations, we use a 2-sample t-test. Well, what happens if we have more than 2 samples that we want to compare? Well, in that case, we have to go above that. We're going to do this ANOVA test. Now, you could do multiple two-sample t-tests. So if I had 3 populations, say I had populations A, B, and C, if I wanted to do t-tests, so 2-sample t-tests, I would have to do one of them with A and B. I'd have to do another one with A and C, and I'd have to do a third one with B and C. So I'd have to do 3 separate tests. And the problem is when I do those tests, the significance level I'm using, alpha, it doesn't just stay at whatever we state it's going to be. So say for the hypothesis test between A and B, we're doing a 2-sample t-test, and say we have a significance level of 5%. It means we're only having a 5% chance of making a type 1 error or rejecting the null hypothesis when it's true. Well, that 5%, now when we do AC and compare those, we add some additional probability of a type 1 error. It's not the whole 5%, but it adds to the 5% we had from the A and B. And then when we do BC, we even have more of a type 1 error. So the type 1 error compounds and we lose that 5% level. We're taking more risk than I wanted to. So by doing an ANOVA test, we can set the risk level at 5% or 10% or 1%, whatever we want, and it's not going to change because it's only a single test. Okay, so that's why we do it. Furthermore, what we're going to be assuming in ANOVA test, that it's a 2-sample t-test, but also that we have equal population standard deviations. And remember, when we have equal population standard deviations and we do a 2-sample t-test, that's a pooled t-test. So we pool all the data together from both samples to get some numbers. Okay, so we're doing an extrapolation on these multiple 2-sample t-tests, pooled 2-sample t-tests, and doing this, what's called an ANOVA test. And I had talked about up here that there's only one other factor in the classification. So we're testing the means like I talk about here. We're testing the means. Say I've got 3 different stores and I want to know on average how many people shop at each store each day. And I want to know if their means, the average number of people each day at each store is the same. Well, I'm testing number of people. That's my variable. The factor in that case would be which store it is. So I've got 3 different stores there. I don't know how that switched so quickly. So I've got 3 different stores. The store would be the one factor. So I'm only going on one factor other than just a variable, in this case, the number of people in the store. Okay, so that's why this is a one-way ANOVA, because I've only got that one single factor of classification. Okay, so we've got all that going on. We know what we're doing. Here are the assumptions in order to do an ANOVA test. And they're all going to seem very similar because they're the same assumptions we use for a pooled 2-sample t-test. So we have to have simple random samples. We have to have independent samples. Remember, that means the selection of one sample does not influence the selection of the other sample. We have to have normal populations. And lastly, equal standard deviations. Equal population standard deviations. Okay, if we have all of these, then I can go ahead and perform the test. So we're going to have to assume that we do. Okay, here's how the test is going to go. We're going to find the F value. Now, I will tell you, in most of these problems, they give you a ridiculously small sample from each of these populations. And the reason why, in order to find this F value, it's very complicated. There's a lot of stuff going into it. Luckily, we don't have to do that. We can either do it on StatCrunch, is what we're going to do today, or you can do it on the TI calculator. The 83 or the 84 is really easy to find. Okay, so we're going to find the F value, and by find, again, we're going to use technology to do it. But here's what the F value represents. It's the variation among the sample means. Because remember, what we're trying to do is we're testing to see if the population means are equal or if there's a difference. Well, so we start off looking at the variation among the sample means. If they're very close together, it leads us to believe that the population means are probably very close together. If they're very far apart, the samples, the means, then the population means might be far apart as well. But notice what we're going to have is we're going to have a fraction, that's the numerator. So the further these are apart, the bigger the F value is going to be. What we divide it by is the variation within the samples. And this is where that pooled idea comes in. Essentially what we're doing is we're doing this. We'll say approximately. So the variation among the sample means, we're looking at the variation, we'll call it the change in X bars. I'll put an apostrophe right there, even though that doesn't really go. So we're looking at how far spread out the sample means are, divided by essentially how spread out the sample standard deviations are. So that's how we would measure the variation within the samples, look at all the standard deviations. And in fact, they're pooling those, so it's looking at the standard deviation of all of the groups put together. But that's essentially what's happening. And then calculation-wise, here's what's going to happen. We've got this F curve. Remember, it's a right-skewed curve like this. We're going to find that F value. And from that F value, we look to see what the area is beyond that. Because remember, the numerator of the F is the variation among the samples. So if that's 0, if all the sample means are the same, then we're going to have 0 way over here to the left. It's going to be a very small F value. There's going to be a lot of area to the right. Well, that area to the right is my p-value. That p-value again is going to represent the probability that we would have gotten our sample results if the population means were equal to each other. And so the bigger F is, the bigger the variation in the sample means, the less likely the population means are going to be equal. Again, the computer or the calculator is going to calculate this for us. It's going to give us the F value, it's going to give us the p-value. We're going to go straight to our conclusion in our hypothesis test. So that's basically the idea. That's what we're doing. And then from there, that's essentially the end of this section. We're just going to go into the last section. I'm going to tell you how to set up the hypothesis test, and we'll do one. All right, so let's go into this last section. So 16.3, One-Way ANOVA, the procedure. Well, it's a hypothesis test that we're going to do. Just like any of the other hypothesis tests, we're going to come to the same type of conclusion, but our null hypothesis is going to be mu1 equals mu2. Remember, I have more than 2 populations that I'm testing the mean of. So I have at least a third mean that I'm doing. And if I had 5 populations that I'm comparing, I'd say mu1 equals mu2 equals mu3 equals mu4 equals mu5. So I'm going to do it with 3 of them. We'll put here, assuming 3 populations. So if there's more than 3 populations, then you'll have to put equals mu sub 4, mu sub 5, however many you have. Okay, so that's our null hypothesis. Sometimes they'll even say all means are equal. Either one. They're both common. The alternative hypothesis, here's where you have to be careful. I cannot say this, mu1 not equal to mu2 not equal to mu3 as my alternative hypothesis, because think of what's happening here. If our assumption is all the means are equal, what would make that not true is if we could find at least one mean that's not equal to the others. So we may have 7 means that we were saying are equal. 6 of them might be the same, but one of the 7's different. Well, the way the alternative hypothesis here, it says none of the means can equal. That's not what we're trying to say. So I can't write the alternative hypothesis that way. The way I need to write it, there's 2 options that are both commonly used. One is not all means are equal. And that's what our book uses. Some books will be more specific and say at least one mean is different. So I've seen different authors like to do it differently, but those are both very common ways of stating it, depending on which one makes more sense to you. But do realize either of those are appropriate. So what I have in parentheses are all alternative ways of doing it. I'm going to list it the way I've just written it originally. mu1 equals mu2 equals mu3, and not all means are equal. Okay, so that's the basic idea. And again, make sure that the assumptions, the 4 assumptions that I said in the last section, make sure you follow all those. And then, as always, having a little trouble writing always, as always, if P is less than or equal to alpha, reject the null hypothesis. And remember the saying, if P is low, the null must go. If you're still having trouble with understanding the p-value and when to reject the null hypothesis or not, make sure you go look at my other video on YouTube that talks about the p-value and how to interpret the answers. Okay, so we'll go from there, and let's just go ahead and do a problem. I'm going to jump straight from here into one of the problems. So let me pull up a problem out of our homework. So let's go in here and go into homework and exams. We'll go into chapter 16. And let me pull up problem 3. There's only 5 problems in this section, so it should be pretty quick. 3, 4, and 5 are all hypothesis tests. 1 and 2 are theoretical questions. Okay, so let's pull this up and see what this problem's all about. It said copepods are tiny crustaceans that are an essential link to the estuarian food chain. Marine scientists designed an experiment to determine whether dietary lipid or fat content is important in the population growth of a copepod. Independent random samples of copepods were placed in containers containing lipid-rich diatoms, bacteria, or leafy microalgae. There were 12 containers total with 4 replicates per diet. 5 gravid or egg-bearing females were placed in each container. After 14 days, the number of copepods in each container were given to the right. At the 5% significance level, do the data provide sufficient evidence to conclude that, and let's write this down, provide sufficient evidence to conclude that a difference exists in the mean number of copepods among the 3 different diets. Okay, so the variable that we're talking about is how many copepods exist. The factor that we're talking about are the 3 different diets. So the factors are the diatoms, the bacteria, and the microalgae. So we're only testing the mean number of copepods based on those 3 factors. So that's a one-way ANOVA. There's only one thing that we're using there to do that classification. Okay, so let's look and let's write out the problem that we're doing. So notice there's 3 of them there. So when we write out the null hypothesis, it's going to be mu1 is equal to mu2 equals mu3. The alternative hypothesis is going to be not all means are equal. And let's see what the author of this problem put down so that we can check and see what our answers we're going to select are. So the null hypothesis, not all the means are equal. That's not a null hypothesis. None of the means are equal. Neither is that. At least 2 of the means are equal, or all of the means are equal. Well, notice he's using that alternative version. All of the means are equal, which we said mu1 is equal to mu2, which is equal to mu3. Those mean the same thing. So we'll select that one. And the alternative, none of the means are equal. That's if we had a not equal between all of them. At least 2 of the means are equal. No, because that could mean 3 of them are equal. That's the same thing as the null hypothesis, possibly. All of the means are equal. No, that's the null hypothesis. Not all the means are equal. There it is. All right, so we'll check that answer. We're good to go there. Let me clear the drawings so you can see, hey, excellent. I like it. Now, conduct a one-way ANOVA test on the data. What is the F statistic? So now we're going to find the F statistic and the p-value like we talked about. So what we're going to do, I'm going to do this using StatCrunch. So over here next to the data, let's click to open the data and we'll open it in StatCrunch. So it opens it up. The data is already there for us. We just go straight into Stat and we're going to go down to ANOVA, one way. And it says, what are your selected columns? Well, we want to select all of them because we're comparing all 3. Now we have to figure out, can I just pull this over? We've got diatoms. That's only selecting one at a time. That's not helping me out. All right, so let's do this. I have to flip over my computer so I can hold down. Good heavens. Okay. So let's do this. We'll go back here. So I'm going to select diatoms. I'm going to hit Shift and then click on microalgae and it'll select them all. Oh, and it even tells you right there, select more than one with Shift click or Control click. So remember, Control click, it'll pick one at a time, but Shift and click will pick everything from the bottom to the top, whatever you're listing. Okay, so I've got all of those, and I'm going to say, yeah, I don't really want any of these graphs or anything else. So let's just go ahead and compute it. Oh, I didn't want that. All right, so let's compute. And we've got right away ANOVA. There's our F statistic right here. Let me jot that down. Let's see, I'll just jot it off to the side on a piece of paper so that we have that. I don't know how many places it wants to go to, but it's 47.8065. I'm sure they're not going to go past that. It's 656, so we'll just call that, well, I'll just put 656 so that I know the next number after that's a 1, so that wouldn't change anything. Notice the p-value is less than 0.0001. Really small. All right, so let's see. So now let's go back. So we've got all that. I'm going to, well, let's just click here and we'll open up the homework. Okay, so here's our homework. Let's make that full screen so you can see it. Okay. The F value, well, let's put in what we got. And I had 47 point, and then we'd go to 2 decimal places. So it's 806, so 81. And we'll check our answer. Fantastic. What's the p-value? Now rounded to 3 decimal places. Remember, it was less than 0.0001. So to 3 decimal places, just 0. You could put 0.000 if you want to, but I'm just going to put 0. And it says, yeah, you're right. Okay, now I'm going to write up the conclusion. Remember, I always recommend you write up the conclusion rather than just pick things. It's too easy to pick something that's wrong because it sounds good. And then you see it's wrong. It's like, oh, yeah, I knew that. So let's write this up. Here's how we'd write this up. So we're going to look at the p-value, which in this case, we're going to say 0.000. Or you could just put 0. We're testing to see if that's less than our 5% significance level, which is alpha, which it is. So since it's less, we reject the null hypothesis. Remember, that's essentially saying, it's not really, but essentially saying there's 0 chance that the null hypothesis is true. And again, my video explains a little bit better than that, but reject the null hypothesis. So we're rejecting that all the means are equal, and we're going with the alternative, not all the means are equal. And so we would state that. The question is, do the data provide sufficient evidence to conclude that a difference exists in the mean number of copepods among the 3 different diets? And we would say yes. There appears to be a difference. In number of copepods among the 3 different diets. And I know some of you are saying, why are we going to write this all down when we just need to pick the right one? Well, I'm writing it down because if your test isn't on the computer, then you can do it. And plus, once you've got it written down, it's easy to pick the right answer. Okay, so let's see. So since the p-value is less than the significant level, reject the null hypothesis. The data provides sufficient evidence to conclude that the population means are not all the same. Simple as that. I'm going to, well, we'll check the answer and then I'll erase what we have so that you can see it. And notice we got the answer right. It's as simple as that. So the good thing about ANOVA, once you understand what you're looking for, when you have technology especially, it's very easy to do, especially since we've had so much practice doing the different types of hypothesis testing. All right, so that's it. I'm going to end here, but keep up the good work. This is the last material this semester. So you've made it all the way through. Fantastic. Congratulations. And best of luck to you the rest of the semester in this class and all your others.